Hello, thank you for joining us today, everyone. It's 11 o'clock, so we'll get started. My name is Gabriel Blevins. I'm a manager of training in the Mobile Solutions Aftermarket Group at Donaldson Company. I lead the Donaldson Training Academy, among other forms of training. In today's webinar, Matt Graham's going to cover some great information about contamination in hydraulic circuits, how to effectively use offline filtration to solve problems and the benefits of applying it, and finally, how to identify the right filtration solution for you. This educational webinar may fulfill some continuing education credits. You will receive an email after the event with more information and a request a certificate of completion. For those unfamiliar with Donaldson Company, we are a filtration company that's been solving complex challenges and protecting customers' valuable investments for over 100 years. And we continue to advance filtration for a cleaner world. Today, we are one of the largest providers of unique filtration technologies, and we excel at producing high-quality filters and parts. We pride ourselves as having a global reach with a local touch. Our world headquarters in Bloomington, Minnesota. We have 55 manufacturing plants and 11 distribution centers around the world to support our customers. Before I introduce Matt, I'd like to quickly explain how to engage during this webinar. As you think of questions, please type them into the chat box and Matt will answer them at the end of the webinar. You're going to find a chat box down in the lower right-hand portion of your screen, so I encourage you to go ahead and click on that to get that chat box open. During the webinar, you can respond to quick questions by clicking on the face icon at the bottom of the screen, so that's to get some quick reactions. There will also be 2 interactive questions during this webinar that you can access on a panel that's going to come up on the right side of your screen. You'll see that when we get to it. Now I have the pleasure of introducing our speaker today. Matt Graham has over 10 years of experience in hydraulic and bulk fluid applications. Working with major outfits throughout the US and Canada, he assesses filtration quality and develops innovative solutions to protect Donaldson customers' bottom line. His work ensures that heavy operating equipment meets specification and quality filtration requirements, ultimately optimizing systems, improving performance, and extending equipment life expectancy. So to better understand today's audience, we'd like to know how familiar you are with the concept of offline filtration in hydraulic systems. So you'll see the poll question come up on the right. I encourage you to please take a moment and go ahead and click on the answer that best describes you. All right, looks like we've still got some answers coming in. All right, it looks like many of you are familiar and some not familiar at all, which is fantastic. This is some of the material Matt's going to be covering today, and I'm very excited for it. So now I'm going to pass it on over to today's presenter, Matt Graham.
Hello, everybody. Thanks for taking the time out of your day to sit with us and discuss a bit about hydraulic offline filtration. But before we get into that, I want to take a step back just to talk about hydraulics in general. Hydraulic systems are really the workhorse of many industrial and mobile machinery throughout the markets that we work with. They transmit power through pressurized fluid, enabling functions like lifting, pushing, and controlling movement all over a piece of equipment. However, there is a silent threat that really lurks within the system, and that is the contamination of the hydraulic fluid. Now, if we take a look at why hydraulic components fail within a system, there's quite a few different things that can lead to a failure. But when we get to the root cause of it, over 80% of the failures that occur within a system are due to oil contamination. And that is a pretty high concentration of those failures, leading to just one of those components. The effects of that contamination in the hydraulic fluid are really far-reaching. They can reduce the efficiency by increasing friction and wear, leading to higher energy consumption and slower operation. Contaminated fluid can also damage components. Abrasive particles like dirt and metal shavings can wear down pumps, valves, and cylinders, leading to malfunctions and premature failures. Water and other contaminants can accelerate corrosion, further reducing the lifespan of these components. And in severe cases, contamination can cause a complete shutdown or a failure, resulting in significant downtime and repair costs. So what are some of the types of contamination? Well, air and water can severely impact the equipment cycle time and performance, resulting in loss of power, reduced heat dissipation, and milky fluid can often look like water or air and causing a foaming condition. Chemical contamination can arise when hydraulic fluid begins to degrade or oxidize and break down. It can also happen if different hydraulic fluid types are mixed. Incompatible additives may have unwanted chemical reactions, and chemical contamination is a primary reason to change your hydraulic fluid regularly. And last, but definitely not least, is particulate contamination. This is responsible for much of the visible damage to final drives, hydraulic motors, cylinders. That sand, silt, and dust, and potentially soot, typically reach that hydraulic system through leaky seals or lack of breather filtration. Even though particulates account for the majority of contamination within a hydraulic circuit, it's arguably the segment that we have the most control over. So when hydraulic filtration is applied to any type of a circuit, there's a few things that need to take into consideration when applying that filtration. Pressure, flow, what that fluid viscosity, what the cleanliness expectations of that circuit are, but then also the working environment. Filtration applications are chosen typically around these different capabilities within that circuit, but unfortunately, if any of these items are overlooked, the fluid might not be as clean as required for that circuit to operate properly. And that's really where offline filtration comes into play. So for those of you that might not be familiar with offline filtration, kind of take a second here to walk through it. So the example we here has is an excavator boom, and you can see that typical hydraulic circuit. Our fluid is moving through the pump, goes out through a control valve, and moves or articulates whatever's on the end of it, and then that fluid comes back to tank. But much like we talked about, if maybe the flow or the pressure wasn't taken into account, or maybe even the operating environment for that piece of equipment is dirtier than what was maybe intended, our filtration may never keep up. And here's kind of a 2D representation of that same excavator boom on the left, but our fluid's coming up, going through a control valve, moving some type of actuator, and then heading back to tank. What offline filtration does is allow us to clean that fluid without interrupting anything within that circuit and without changing or augmenting any of the performance within that hydraulic application. So the question is, next question, you should have a pop-up come up, is what is the biggest challenge you face with hydraulic system maintenance? There's a couple answers there. Feel free to plug those in, and we'll give you guys a minute to enter in those answers. The answers come in here. It appears that kind of the top two are the contamination of hydraulic fluid and also downtime and productivity loss, with high maintenance coming in at towards the end there. So I appreciate you guys' input there. We'll continue on. So when would we use offline filtration to solve some type of a problem? There's quite a few different categories that we typically look at for this. One being if dirt or water ingression is not preventable. And a lot of times that is probably the top choice. So we think about pieces of equipment, they get built, manufactured, and then they go out and perform their duties. Most of the time, those duties aren't in sterile environments. Like this picture here, we have a large dredge. You're on water. You're going to be dealing with some kind of water ingression. Or maybe you're in a very dirty environment, so like a steel mill in the basement where we've got continuous amounts of dirt ingression and moisture that can get into that system. Or maybe ingression is happening at a faster rate than to be filtered out on a normal circuit. We have filtration in place with these circuits, but if that ingression is happening at that faster rate, we're never actually going to get in front of it. Or maybe we're unable to modify the current circuit on current filtration on that circuit. This is pretty common in mobile equipment applications where body panels or different things are configured in a way where augmenting or changing the filtration within that circuit would be very cost effective or uncost effective, excuse me. Or maybe we're looking to increase drain intervals. A lot of times fluid is replaced because it's become too dirty to be able to be used, but the actual additive packages and the chemical makeup of that hydraulic fluid is still fine, but it's too dirty. Or even the transferring of new fluids, whether that be fuel or bulk lubricants, making sure that those fluids are cleaned as well, and we can use some of those offline filtration principles to solve that. Next, I wanted to go through a couple examples of where we've applied offline filtration to help that benefit for whoever is operating those pieces of equipment. First, I'd like to take a look. This is a stationary example of a cold roll steel facility. In this location, what you're looking at there on the screen is actually the spool valve inside of a D10 valve. At this facility, they were replacing these valves bi-weekly, and their downtime at this mill was about $6,000 per minute. Their total monthly cost of failures, including the downtime and replacement of these parts, was totaling a little over $350,000 per month. We installed some changes to this facility, added some offline filtration. In the next 24 months, we had no valve replacements, and we had no unexpected part replacements in that same time period. What that looks like, implemented, added a couple filter panels on some of these units. We did implement an oil analysis program so they can continually monitor that oil and the health of that. And even including the filter element replacements per month, that provided a cost savings to that facility of over $300,000 a month that they were able to put back into their bottom line. And if you're familiar with ISO cleanliness codes, you can see that chart there on the bottom. It reads right to left as far as timeline goes. But we were very dirty, and we were able to clean that up by almost over 1,000 times improvement, which ends up leading to that cost savings at that facility. Next example I wanted to share with you is a mobile example. So this is on a frac rig power end. So one of the things with frac fluids is they are exposed to extreme amount of moisture and particulates that can make their way in. And downtime is something that is a big concern. So we added offline filtration to this. We were able to clean that fluid without alternating that current circuit whatsoever. We were able to reduce the amount of failures and increase that time between replacement of that power end. And this really can apply to anything within that circuit. It can apply to power ends, hydraulic fans, and anything within that. So we took a sample of the fluid beforehand, and that is this oil sample that you see there on the left. Just as kind of reference, that green hazy line that you can see is printed on the patch to be able to identify how big your particles are, but you can hardly see it with how much particulate is there. Realistically, the cleanliness in this circuit was over that 26 that you see. The right-hand side of the screen is what the target cleanliness level is for that piece of equipment in order to operate without causing damage to that circuit. So we're over 64 times dirtier than what the target is of a 20 there on the right-hand side. And that's a sample there of after that fluid is being maintained by a filter panel. And again, if you're familiar with ISO cleanliness codes, the target is to be between 500,000 particles per 100 milliliters, and where they were at was over 32 million particles per 100 milliliters, a substantial amount more of dirt within that circuit. I don't know if anybody's familiar with the life extension table. This is a table, if you're familiar with Noria Corporation, they do a lot of testing to be able to figure out what the difference in life length a piece of equipment will be able to yield depending on the dirt level that's within there. But if our current ISO cleanliness code is at about a 26, and we're able to get it down to about a 20, that results in roughly a 3x component life extension for that piece of equipment. So let's look at what kind of that return on investment would be in order to be able to achieve that. So the current filtration within that power end was yielding about a 6,000 hour power end replacement. And the power end replacement for one of those pieces of equipment is roughly right around $65,000, give or take. So that equates to about $173 a day to operate that piece of equipment. We added filtration panel to that power end. And instead of having that 6,000 power end life cycle, we're able to get it to a little over 15,000 hours. Still have that same $65,000 cost, but the frequency has dramatically reduced. Upgrading costs then moved to about $70 a day. So even after the implementation of the filtration and replacing the elements within that offline filtration panel, that nets out to about $20,000 savings per rig per year. As many of you on the call probably know, there's not just one rig at a facility, and that math starts to add up very fast. Taking a look at the cost over time for that rig, assuming that that piece of equipment is in service for about 6 years, that's about $160,000 per a rig over that same cost savings period of that 6-year interval. And so if we look at that, each peak that you see would be a power end replacement just using the standard filtration that was on that circuit to begin with. But if we implement some offline filtration panels, yes, we do have an incurred cost at the beginning, but we have 2, arguably 3 peaks instead of 6 peaks within that time, cutting the power end replacement interval in half or more. Then one other example I wanted to share is kind of on the other side of an extended drain interval. So we talked briefly about oil getting replaced due to oil contamination and the oil essentially just being too dirty to operate through sampling. So in this application, we had high level of particulates in the oil, and we were draining and replacing that fluid every 500 hours. And that contaminated fluid that was in there was also leading to premature failure in those motors. If you're familiar with the cost of these motors, depending on the piece of equipment, that incurred cost could be somewhere between $250,000 to $600,000 or more. The expected life expectancy, or excuse me, the estimated life expectancy, according to GE, who manufactures these motors, is about 24,000 hours. So again, we took fluid samples here to address where our starting point was. And as you can see on this patch here, again, you can almost make out that green line. But what we have is high amounts of particulates within this sample. Many large 14 micron and larger particles, and you can see that by those shiny spots that are on there kind of glaring back at you. So there's a lot of hard particle material in there as well. So what we did is we implemented, instead of draining and dropping that fluid every time due to contamination, since the additive package and everything else within that fluid was still good, when that piece of equipment was in for its service interval, we'd hook an offline filter card up to it. We were able to reduce those contamination levels by over 100 times and increase that oil change interval by 4x. So instead of draining and dropping that every 500 hours, we're able to get to 2,000 hours of fluid time, dramatically reducing the cost of fluid for this operation. We're also able to reduce the fluid particulates, resulting in a 1.5 to 2.5 life extension of those expensive rear wheel motors. So what that looks like beforehand, using filtration and an offline cart to be able to polish that fluid and return it back into service, we're over 100 times cleaner than those original conditions. So if we're selecting a system, no matter the type of piece of equipment, whether it's mining equipment, mobile equipment, or if it's even a stationary setup, there's a few things that are needed to know in order to select a system properly. We need to know what the reservoir size is. You know, are we dealing with 100 gallons in a rear wheel motor, or are we dealing with 2,000 gallons in a mill application somewhere? We also need to know what that fluid type is to make sure that we're applying the correct filtration that's compatible with that fluid. We need to know what the fluid temperature is. That results in a difference when we're talking about hot to cold in that fluid. It can either be very thick or very thin, and that fluid needs to be, the filtration needs to be applied properly in order to handle the difference in viscosity of that fluid. And then what is our cleanliness level target? And some operations may or may not have cleanliness targets that they're trying to reach. But the other way to handle that is what components are downstream that we're trying to protect, or what is the most expensive component within that circuit, and we can make sure to select the filtration correctly to protect whatever that component is. And then last but not least is that desired time for cleaning. This is especially important if we're using a filter cart in that rear wheel motor example. That piece of equipment may be in for that PM schedule, and it's a 6-hour PM schedule. We need to make sure that we select the flow rate properly to be able to clean that fluid in the time that that piece of equipment is in for service. So where are the most frequent places that we apply offline filtration? Anywhere where we have frequent downtime applications, right? If there's something that is causing downtime habitually within that system, typically we can offer offline filtration solutions to minimize that. Maybe we're replacing hard part components outside of the schedule, right? This piece of this component is expected to last 5,000 hours, but we're getting 1,000 to 2,000 hours. Those are applications that we can focus on. Maybe we're replacing the fluid frequently due to contamination. We pull oil samples and that fluid's not meeting the specs of where it needs to be anymore. A lot of times we can help that out by using filtration to solve that problem. Maybe we have water contamination issues. We're in a high moisture environment, or maybe we even have seals within a component that are leaking, but we know we're not going to be able to take that machine down to fix it for some time. We can add filtration to that circuit to be able to remove that and keep the equipment operational. Maybe we're not meeting cleanliness targets. You know, if we're doing oil sampling, we get our samples back and the dirt content is too high for what we want it to achieve. In many cases, the knee-jerk reaction is to put a tighter filter on there to clean that up. The unfortunate downside of that is we might be actually putting too restrictive of filtration in that circuit for it to either operate properly, or that bypass valve will open and just allow dirty fluid to continually circulate in there. And last, rapid filter plugging. This is one that we kind of typically overlook a lot, I feel. But if we have a circuit where the filter is continually plugging up and we're having to change that filter more than we'd like within that system, a lot of times it could be undersized, or a dirt ingression level is too high to be able to combat with that filter that's in the circuit. So adding offline filtration or a kidney loop card or a filter card for that application can help reduce that rapid filter plugging that maybe we can't solve within that circuit correctly. Overall, kind of key takeaways for offline filtration is, number one, reducing that downtime, right? That's costly, and anything we can do to minimize that can be a good application. For kidney loop or offline filtration allows for that cleaning the fluid without impacting the working circuit. If we're having some issues with that circuit, maybe it's in a way where it's going to be troublesome or problematic to be able to alter that filtration within the current circuit, adding a kidney loop or offline filtration is a real easy way to be able to yield results without augmenting anything in the circuit. We can increase fluid drain intervals. We can extend system component life. And last, but definitely not least, always remember that new oil is new, but it's not necessarily clean. So we can use filter cards to be able to transfer that fluid into those circuits without causing any damage to them by adding particulates to that circuit. I appreciate your time. I'd like to open it up now for what questions or any discussions that we might have from anybody that's on the line.
All right, thanks, Matt. We did have some questions come in over the chat, so I'll start reading a couple of those to you.
Sure.
We have first one is a comment and a question from the same attendee. So I'm going to read the comment first and then get to the question. And the comment was, manufacturers recommend much longer servicing times that users have to follow. And the question tied to that is, why are these servicing on hydraulic systems so often made at ×2 or ×4 the hours of a normal engine filtration servicing interval?
Yeah, that's a really good question. It really boils down to the contaminant ingression that occurs in an engine application. Remember that blow by from that combustion cycle is normal and is part of that. So you'll get soot and things that drop out into that oil. You're also really hard on that oil too. We're high temp applications and we're really pushing that to its limits, and you start to get breakdown within that fluid in the engine oil process. Now in a hydraulic circuit, you have some of those, obviously those same pressures and those same temperatures that can occur, but typically we do run a bit cooler, and so we don't oxidize nearly as fast, and we don't have those combustion type contaminants that are pushing by the pistons and making their way into the fluid. There's other contamination issues, obviously, but that fluid typically can last longer in a hydraulic circuit just due to the environmental nature of not seeing combustion gases and not seeing those higher temps. So they will typically be able to last longer in a hydraulic circuit.
Great, thanks, Matt. Here's another great one. Can you elaborate on the different types of contamination and how they impact the hydraulic circuit and performance?
Yeah, let's start, I guess, with water. When we look at water within a circuit, there's quite a few different things that can occur. Water, one, is compressible a bit. And so you'll get, if you have water within a hydraulic circuit, you will get a little bit of squishiness potentially in whatever you're trying to operate, especially if it's a cylinder-based circuit. Air will do something very similar to water when it comes to being compressed. Air compresses much easier, so you might get soft or spongy. But you also can potentially cause cavitation in the pump, which can start to wear out that pump. Those little air bubbles that are all mixed within a fluid can collapse during that suction, the pressure cycle, and you'll end up with what almost looks like kind of sandblasting on the edges of fins of pumps and tightly machined surfaces. Going back to water too, you can also cause corrosion issues within that circuit and have all sorts of different issues with water. Chemical contamination, if we just take a look at, the oxidization cycle, if you've ever heard or, varnish being thrown around or something that kind of looks in that realm of that kind of tainted looking plating out of varnish on components, that rapid oxidization essentially is allowing that to occur. That can cause stickiness in valves. It can plate out on all sorts of different things, cause valves to stick, and that piece of equipment may not move properly. It can also cause heat spots or hot spots on different components and cause them to wear out faster. And then particulates, kind of the best way I think about it is at a macro scale, if you added sand to something, you're just allowing that sand to sit there and wear back and forth. And that grinding back and forth of sand within that fluid between machine surfaces is going to create more little particles that end up coming out, and you start to accelerate really fast when you have particulates within that fluid. You accelerate the wear of those machine surfaces and can cause issues with that.
Awesome. We got another great one here, and this is a very common question. I'm glad somebody asked this. How do you determine the right filtration solution for a particular hydraulic circuit?
Yeah, great question. The first thing I typically take a look at is what is that circuit doing? And what I mean by that is it a lubrication circuit that's moving fluid around for some type of heat transfer or lubricating a bearing or something like that? Is it going to a cylinder? Is it going through maybe a really tight tolerance valve? And really that comes down to then being able to identify what the tolerance is within that circuit. The tighter the tolerance, usually the higher the pressure, and usually then the more susceptible it is to dirt. And that gives you an idea of, all right, how clean do we need this fluid? And then what type of filtration would we apply? So for an example, if we had a gearbox that we were trying to make sure stayed to a specific cleanliness level, we'd choose a different filter to solve that problem than we would if we were talking about a high pressure hydraulic circuit that has servo valves. We'd choose different filtration for that. And then there's also different chemical compatibilities. So if we have regular petroleum-based hydraulic fluid, that might take a certain type of media. And then on the other side of that, if we're looking at a water glycol-based fluid or maybe a flame retardant fluid, we would use a different media grade to be able to tackle the particulates within that fluid as well, and making sure that we're staying within that chemical compatibility range.
Great. Next question. Another good one. What are some common symptoms that a hydraulic circuit is contaminated? And then what immediate actions should I take?
Yeah, great question. So let's start out with if you have water within that circuit, draining that out. If it's a lot of free water in the base of it, draining that water out and getting rid of it. There's kind of a teeter-totter of where it makes sense to just drain and drop and replace that fluid versus trying to correct it and remove that water fluid. Remove that water from the fluid usually depends on the volume. You know, if we've got a 5 to 10 gallon reservoir with some water in it, it's probably cheaper to drain and replace that and clean that water out than it would be to use filtration to remove that from a time and money standpoint. If we have a large reservoir where, say, we've got a couple thousand gallons worth of fluid, that can get quite costly in order to replace that fluid. And that's typically where filtration will be used to remove that and get it corrected, as long as that fluid's additive package is still within in the correct specifications. Particulate side of it, if we're going to apply that filtration to it, we kind of look at some of the same things, but most of the time we would use that filtration to remove those particulates. You'll start to see before that some contamination issues. If you're doing oil analysis, you can see those things start to creep up. But particularly you'll see the failures of components that will start to creep up, maybe valves that are failing, seals that start to leak. It's usually a pretty good indication of over-contaminated fluid. And again, I guess we go back to the drawing board and see what type of circuit, what type of fluid, how clean we're trying to be, and then appropriately size that offline filtration or kidney loop circuit to be able to deal with the contaminants we're trying to tackle.
Great. Next question. How often should the filters in an offline filter circuit be replaced, and how do I know when to replace them?
Great question. And it's really the same answer as it would be for online filtration or filtration within that circuit. So we always want to replace filtration based on restrictions. Typically within a hydraulic circuit, there's bypass valves that will open up once that filter starts to be loaded. And an offline filtration situation is really no different. There's going to be bypass valves in there that will open up to not destroy the pump and cause issues. So most filter carts, offline applications, whatever it may be, will have some type of an indicator on that head or on that circuit to tell you when that filter has reached its maximum restriction or the bypass valve is starting to open, and we want to make sure to replace the filters on whatever that application is based on those restriction indicators. That's going to be the best way to make sure that you're getting the most bang for your buck as well. If you replace filters too early, you could be just kind of throwing money out the window of, hey, that didn't need to be replaced. It's very far away from its maximum restriction. Or on the inverse side, if we don't replace them when they need to be, you're essentially not really doing anything when you're turning that fluid over and cleaning it, because that valve is open, just allowing dirty fluid to recirculate within that system. So in short, indicators.
Perfect. Next question. How does offline filtration handle different contaminant, such as hard contaminant, water, air, etc.?
Yeah, that's a really good question, and there's definitely different solutions based on the contaminant. If we're going after just particulate, a high efficiency dirt removal element is going to be your best friend for that type of application. If we're trying to focus on water, there's a couple different solutions and approaches that you can take. Water absorption media, which is very similar to like what's inside of a diaper, is going to absorb and hold that fluid, or excuse me, hold that water. But they don't do a great job at removing particulate. And then air, essentially slowing down the flow and allowing bubble nucleuses to start to make bigger bubbles and bigger bubbles to float up to the top. So there's different solutions dependent on the type of contamination that you're trying to deal with. It really kind of depends on each circuit. And that's kind of goes back to one of those things of what are we trying to achieve with this offline filtration or kidney lube circuit, and then selecting the correct filtration or approach for each one of those.
Okay, great. And the next question I'll answer for you, Matt, and it is, can we receive the PowerPoint of this presentation to share with customers? And unfortunately, we cannot give out the PowerPoint. However, what I feel like is even better is we're gonna post this webinar on our website sometime within the next week or so. So you'll be able to access a full recording of this. And then we had another question just come in. What kind of monitoring would you recommend putting into place of an offline circuit?
I'm assuming the monitoring question is from like a fluid cleanliness side of the equation. You can set up a cart to have a particle counter in line for it. I will caution that it is a bit of a gray area. Fluid condition monitors from a particulate standpoint typically are using a photo lens or a laser, and as those particulates go by, they'll block the light and then I'll start counting particles. The unfortunate side is most hydraulic fluids that are used today, especially in off-road type of pieces of equipment, have tons of friction modifiers, anti-foam agents, all sorts of different things within that fluid. And while they're not contaminants, they're soft particles that flow through. Those can trigger a particle counter to report back a higher quantity of particles than are actually there. So monitoring that to get that is fine. We just need to make sure that the fluid that is being used isn't maybe a highly additive or a highly modified fluid, as you might get some false high particle counts within that circuit. You know, my favorite thing is right, as you've probably seen throughout here, is taking a visual pass and identifying what those particles are specifically. That to me is really the best way to get an understanding of what that fluid cleanliness level is within that circuit that you're trying to clean up.
All right, very good. We had another one come in about adding offline to a circuit. So the question is, can offline filtration be added easily to a circuit, and then common mods?
So it depends on the circuit of where you plumb or add it in. I would say over the years, there's very few pieces of equipment where I've said, hey, it's probably not going to work out very well. Almost always there's some type of port we can add, something we can put on or add to that circuit in order to be able to hook up an offline filtration application. So whether it's, a different port that's on the reservoir, whether it's tapping into the return line and allowing that filter to circuit. I've done applications where maybe we've got a reservoir in the basement. Nobody ever wants to go down there to be able to change it, or it's not going to be seen. We'll run plumbing up to somewhere else so we can put that panel in a place where it's easily accessible. There's all sorts of different kind of unique ways to be able to add it to it. So where there's a will, there's a way. Obviously, there is some places where it may or may not work, but in most cases, there's always some type of way that we can figure that out. The kind of second portion of the question about mods, I guess I'm not quite sure what the question is there, but I will say that there's many cataloged options that are out there for filtration. Hey, these are right off the shelf, but like ourselves here at Donaldson, we do numerous amounts of custom panels and different configurations, depending on the circuit and the system, to be able to make sure that those needs are met.
All right. And next question, Matt, can you give a little more detail on the ROI for using offline filtration and some industrial applications?
Yeah, a little bit more detail on that. I guess, specifically for industrial applications, typically kind of start with, all right, let's, for an example, I was working with a company that cut blades for lawnmower applications, so they have big grinding equipment, but the fluid that they're using within it is starting to tear out pumps. So figuring out how many pumps they're going through, what those pumps cost, and what downtime costs, to figure out kind of what that net loss for them is in their current trajectory of how they're operating. Then we take fluid samples before, figure out where essentially that baseline is of where they're operating, and then figure out what the target cleanliness should be for that. So in this example that I was talking about, target for those pumps were 19 or cleaner, but they were operating at about a 24, if I remember. So we had a target, we were going to get them down to an 18. We implement that application. Now that that fluid is cleaner, we use that NORIA chart that we had talked about and showed, all right, we should at least see a 2x extension. And then we can monetarily figure that out. All right, what was their initial cost, the way that they were working? If we reduce those part failures in half, here's where your net, your expected, I guess, expenses would be from adding filtration. Much in the same way, I'll kind of go back to this chart here and helping figure that out. So that gray line that you see, that's the current trajectory. If they didn't change anything, that would be the typical cost run out. If we add filtration, here's what the initial cost would be. Yes, you're still going to have some part replacements. It's how things work, but we're going to reduce those down, and then we can figure out the delta between the costs that they were running before versus the costs that they should be expected to receive after implementing offline filtration. So each one is unique. Each one's different of how much cost savings there are, but there's rarely, I guess, a case that I've been involved with where it doesn't pay off in a pretty short window.
All right, and we're getting close to the end of our questions, so if anyone has any more, be sure and type those in. Got a couple more for now, though. How does the addition of offline filtration change maintenance and downtime of a hydraulic circuit?
Yeah, good question. So when adding offline filtration, let's take the example of like a permanent installation. We're going to put a panel on there and it's going to run 24/7. It's going to do a couple things. first off, it's going to take that pressure off of the inline filtration that's there for the normal working circuit. So say if you were having to replace those filters every 500 hours and they're being loaded really fast, that offline filtration is going to add more surface area to that circuit and take that work off of those filters. You might be able to extend the actual replacement of the filtration with the normal working circuit. Otherwise, what you're also able to do, we talked about extending fluid drain intervals. So the cost of that replacement of that fluid, whatever that interval is, typically is done based on that fluid becoming too contaminated. If we can prevent those contaminants from being there in the first place, we can extend those fluid drain intervals. And then also the added benefit of part cost replacement, right? Parts need to be replaced. Parts wear out. It's kind of how things work. But if we can keep that fluid cleaner for longer, we can extend those part replacement intervals and dramatically reduce that cost of ownership or that cost of operation for whoever is operating that equipment.
All right, thanks, Matt. And I have one more question here. What are the primary causes of contamination? And it's actually a two-part question. And then how does offline filtration address that?
Yeah. So I guess what I will say is it's always cheaper to prevent the dirt from getting in or those contaminants from getting into a circuit than it is to clean them up. So in any case, no matter what it is, it's always going to be cheaper to do prevention instead of cleanup. And so what I mean by that is, let's take, you know, a frac rig in that power end application. Usually we're operating in really dusty, dirty environments, right? And you can get a lot of contamination that'll come in through a breather. So if we can actually change that breather, reduce the amount of contamination that can come in, that can be a really good solution to that as well. So being able to prevent those contaminants before they get in can provide very incremental changes within that circuit by just preventing that from coming in. But that offline filtration and adding that to that circuit can help prevent those same things. So if we're having, you know, high amounts of water within that circuit, a lot of times maybe we can't change or fix or replace what's wrong with that water contamination in there until a certain predetermined time, especially at like a plant location. You usually have to wait for like a plant shutdown in order to do those items. Adding offline filtration to a circuit or a kidney loop to that circuit in the meantime can help maybe keep some of those issues at bay until we can actually fix the problem before that problem forces you to shut down before your expected downtime occurs.
All right, these are great questions, guys. I'm going to give it one last call for questions because that's all we've had come in so far. So if anyone else has one, please type it in now. All right, I don't see any others coming in. We will go ahead and wrap this up. So thank you everyone for participating in today's webinar. Please look for a follow-up email with guidance on how to request more info, a free consultation, or a certificate of completion that you may apply towards continuing education credits. Thank you.